4 weeks and first live session, we covered 4 weeks of this particular course. We got a recapitulation of what we have been studying in the first 4 weeks, which involved the orientation, a little idea about MATLAB coding, what are the strengths, what are the limitations, what are the other tools available. And then we started with 2 labs. Both of the labs involved uh, essentially the use of non-linear algebraic equations. In the first lab, we dealt with a single nonlinear algebraic equation. You must remember that there was a correlation to determine the friction factor. And then in the second lab, we used, in fact, 2 nonlinear equations to solve the problem. In this live session, we will take up from week 5 to 8. During these weeks 5 to 8, we covered the labs, lab number 3, 4, 5, and 6. So what I will do is I will share my screen and we will, with the help of some slides, go through all of the things which you should essentially and quickly remember, and some take-home messages that you might want to have. So I'll share my screen with you. So hopefully the screen is visible. So as you know, I am P.A. Deshpande. I've been teaching you for the past 2 months. And the plan for this live session is, first, we'll have a take-home message, set of take-home messages from weeks 5 to 8. So this course has 12 weeks. In the first session, we took first 4 weeks. Now we'll take the next 4 weeks. Next, as we always do, we'll stop this session by what you may expect in the weeks to come. We will also take some question and answers from the forum, from the sheet which you have been circulated. And during the session, if you come across any specific problem, any question, please feel free to ask. So we started this week 5 with the analysis of multi-component distillation. So I will very briefly recapitulate what kind of problem which we did, what was our problem definition. Then we would realize that to solve this problem, we needed simultaneous linear algebraic equations. These are very different type of equations that we will be dealing, that we dealt with, and finally, how to do the analysis and do the presentation of results. So the system that was in front of us was a very simplified part of a refinery. So I hope you remember that you had a crude distillation unit, naphtha splitting unit, vacuum distillation unit, which you can see 3 columns here. And you were essentially required to determine the mole fractions and output flow rates from all of these streams. So this essentially was the soul of the problem. And then we realized that what all are different things which one may need to account for. We wanted to solve for the equations, the model equations that would come would essentially be linear algebraic equations, and in which the crude feed rate would be one of the parameters, and there is an uncertainty of plus or minus 50% due to various global uncertainties, and we wanted to solve the same problem within this band. How to solve that? And then you also realize that you have 2 types of crudes, Russian crude and Middle Eastern crude, and you have to do testing of these 2 crudes to give you the recommendation of which crude is better. So this was the problem statement. And how do you actually go about solving this? Very, very simple, in a sense, simple material balance problem. Your analysis involves overall mass balance. So these are the overall mass balance equations. all the flow rates were given in terms of mass flow rates. We spent quite a good amount of time in appreciating why it should be mass flow rate rather than volumetric flow rate. And then, apart from the overall mass balance, you also need to do component balance. So you look at each individual component, do a balance, the kind of thing which you study in your material and energy balance or chemical process calculations course. And then you realize that you end up with a very large number of simultaneous linear algebraic equations. So now what we say is that it's possible that you have simultaneous linear algebraic equations, which are essentially of the form which is given in the left hand side, and you can put these equations in the form of matrix, and this in fact is a very good strategy how to solve or how to deal with non-linear algebraic equations by converting them to a matrix equation. The matrix equation is given from the left hand side. And once you do that, what you can do is do a series of matrix manipulations, matrix operations which you study in linear algebra to get the solution. So one of the ways is that you define what the matrix A is, you know what the matrix B is, and then you invert the matrix A and multiply it with matrix B. That would simply give you the matrix X. Matrix X is the vector of unknowns, right? So this was one of the methods. So this was our first problem strategy. But in this problem strategy, you explicitly gave the numbers, associated with all the coefficients which were the elements of this matrix. There, in fact, is another way, which is using the symbolic algebra. So you have symbolic algebra tool, which is available, symbolic mathematics tool, which is available in Matlab, and you invoke that by SYMS X, Y. Define these variables, and you use the function equations to matrix, which means you give equations in a written form, something which is very similar to what you see here, like equations which you write on paper, and then this function equations to matrix converts that into the form of a matrix equation, and then you can again solve. Another way of solving this matrix equation was to use this ML divide operator, where you simply give the solution as division of A, the matrix, divided by inverse of the matrix divided by the vector B. So this is how you learned how to solve the simultaneous linear algebraic equations. And then we were asked to do analysis and present the results. Right. So then we realized that you can always put one command or the other, where you can print the solution on the screen. But it's a good idea, because you have been asked a question, to give proper answer on the screen. And on that basis, you see that here, after complete set of calculations, you could in fact write on screen or print on screen gasoline output at minimum feed rate is equal to, and then you print the value there. So this is a very nice and presentable way of showing your results. Then you were also asked with another question, that what would be your recommendation if you change one group to the other, which would maximize one given component of your string. Now, this was again an exercise where you change the entire matrix and then redo the calculation using the new matrix. The matrix comes from the composition of the group. So then you must have learned that you can save these compositions in the form of numbers in an external file, and then you can read that file and do the calculations as many times as you want. So this is a very nice way, ingenious way of making your code, that you don't disturb your original code, yet you do the calculations again. Now, in the next lab, so now in the previous lab, lab 3, we learned a very different, a very new technique, the technique of handling non-linear simultaneous algebraic equations. In lab 4, week number 6, we started with a completely new category of equations. The equation was a ordinary differential equation. To understand how to code an ordinary differential equation, what we can do is we can in fact take an example of a dynamical system, and what we did was study the cooling of a sphere in a reservoir. So we would first spend some time in understanding the system, what all can be understood by the system, what is the solution strategy, because we have a new type of equation, and then based on what has been asked to you, how best can the results be presented. So the system that was in front of us was that you have a reservoir liquid which had a constant temperature. The temperature of this liquid won't change, and that's why you are saying, referring this to as a reservoir, and the temperature was maintained as T infinity, and a solid body at initial temperature of T0 was dipped in the liquid reservoir. As you would see from here, the model equation is known to you. This is, first of all, a differential equation. Second, this is an ordinary differential equation. Third, this is a first order ordinary differential equation, which means that this is going to be an initial value problem. So if you know the value of temperature at a given instant of time, then the value of temperature at future instance of time can be calculated with the help of this equation. Right? So now what all could be such problems pose in front of you? You may want to determine the temperature, the time requirement for the temperature of the body to drop to certain value. It starts from some higher value. Second, there are several parameters, there are several material properties which are associated with the system, and that may affect your dynamics. For example, heat transfer coefficient, surface area, density, specific heat, so on. So these are the parameters. These come from the properties of the system. And if I change this, how is the rate of change of temperature, and how is the dynamics going to change? Then, what if I give the system certain kind of a RAM? So the reservoir temperature itself is not constant, but it changes with time. The equation being given as the reservoir temperature gives us T infinity, the initial temperature of the reservoir, plus 0.52 times the time. So it's a linear increase in temperature with time. So under such condition, when the reservoir temperature is not constant, how would the temperature change? And finally, we learned a completely new concept called phase portrait. So first of all, we must realize that in principle, it's possible to solve the problem because this is a relatively simple equation by pen and paper method, and therefore we got an idea how the solution would look like. So we wanted to make sure that our numerical solution, in fact, has this trend, right? So we made the code, and the first and the most important thing is how to solve an ordinary differential equation initial value problem. So then you would realize that there is a function here, ODE45. ODE45 is an inbuilt function which tells you how to solve an ordinary differential equation initial value problem. We must realize that this function solves an initial value problem like the one which is currently in the consideration. Now, once this is the case, we don't simply have to determine the evolution of temperature, but we need to determine the time at which a particular temperature is reached. So therefore, we did a lot of ingenious jugglery to determine, to invert the problem of not determining temperature as a function of time, but time for that temperature to be reached, right? And therefore, we also used an interpolating function to make finer time discretization, and then we got the solution. But then the information which you need to solve ODE45 is the actual definition of the function. And the function definition is nothing but the derivative definition which comes from the problem. So we defined the reservoir function which goes in the ODE45, and here you will see that df is basically nothing but dt by small t. This is the definition which has come from your original problem. So you solve this problem in two blocks. In one block, you define what your problem is, that is this block, and you solve the ordinary differential equation, which is this block. So while you solve this problem, if you remember our original solution, which came from analytical solution, pen and paper solution, there is a non-linear exponential decay in temperature. We in fact got this decay for all the cases. This is one particular problem where you had to change the value of the specific heat of the system, and this is how you saw and presented the results. Presentation of result is important, so you have learned how to put these, apart from putting proper curves with proper thickness, color, legends, and so on. How to put this text and arrow to show the proper trend in the system. Next, very interesting problem. When the reservoir temperature itself changes. So in the right side, you see the red curve, the flat horizontal curve is a curve which shows that you have constant reservoir temperature, and when the reservoir temperature is a constant, the sphere temperature keeps dropping monotonously. Expected. But then when the reservoir temperature starts increasing, if you see here on the right hand side, after 45 seconds now, the reservoir temperature is increasing at a constant rate. The body temperature tries to catch up, right? So therefore, body temperature also starts rising. First it reduces, then it rises again. Finally, the meaning of phase portrait. Phase portrait shows a family of solutions. It doesn't just show one particular solution corresponding to one particular initial condition, but all possible solutions. And then therefore you would see that for various initial conditions, you get this family of curves. In fact, with the help of code, you can make these lines, phase lines, more and more fine. So this is something very new which you must have learned. Next, extension of ODE IVPs, where instead of one IVP, we use two IVPs. Right? So the system was unsteady state operation of a cascade CSTR. We went through the same procedure, we defined the problem properly, had the solution strategy in our mind, and presented results very properly. So a cascade CSTR system, chemical engineer, we know and understand how this works, except that we are not simply dealing with the steady state operation, rather we are dealing with the unsteady state or transient operation, such as CSTR. So how does the concentration evolve with time if such a CSTR is used, right? So that's the basic idea behind this. So you had to determine the evolution of concentrations of A and B in both the reactors in the first 10 minutes of operation. Secondly, the time requirement to reach steady state, and this was an interesting exercise. We'll see how. And finally, the effect of various parameters of the system. So then you see this problem is in fact, the problem remains a dynamical problem which involves first order ODE, but not one ODE, rather four ODEs. Right? So when you have four ODEs, what essentially is going to happen is you need to solve these four ODEs simultaneously. So what's the strategy? Well, then you realize that the function remains the same. The function is in the ODE 5, but now what you need to do is you need to define a vector. You need to define a vector and all the unknowns. What are the unknowns? CA1, CB1, CA2, CB2. These all unknowns become the components of the vector and the vector becomes the unknown. Right? So here, if you compare the syntax, it remains unchanged. But then you have to define instead of an unknown, a vector whose components are unknowns, and therefore initially when you used to give an initial condition, now you have to give an initial condition vector. So here this problem initial concentrations for the four species were set to be 0. Right? And then you will see that more or less the entire procedure remains same. You see here, you define a vector and you define individually all 4 equations. Okay. Now, determining the steady state is an interesting thing. So this can be done in 2 ways. So in a transient operation, the concentrations would evolve, and at some point of time, the concentrations will become the change of concentration will become 0 with time, which means the concentrations will become constant. Now that's the steady state. So what you can do is you can keep on evolving the system and keep on checking whether the concentrations have become constant or not. So that is what was the first approach, where you solve all 4 equations you did previously, not for a given not up to a given instant of time, but you keep evolving the time. You stop when all 4 become constants. So this is exactly the method which we follow. So then you would realize, and therefore you have to do the time evolution of concentrations. In the second approach, here what you can do is you see here that dCA by dt is equal to f of CA1 and so on. This must become 0 at steady state. Similarly, dCB1 by dt must become 0 at steady state and so on. So at steady state, all 4 terms individual, all 4 equations individually must become 0, and then in that case you will realize that you have simply a differential equation. You have an algebraic equation, in this case linear algebraic equations, and you can simply solve linear algebraic equations, or in case you get non-linear algebraic equations, then also you can solve simultaneous non-algebraic equations the way you solved them in the previous labs. So that is what we had done. And then you will realize that you see all kinds of evolutions. There were 2 parameters which were important, the rate constant and secondly the space time. So as you vary the space time, what happens to the concentration? What happens to the concentrations in various reactors of different components? As you vary the rate parameter, what happens? The evolution, in which case the steady state is reached quickly, in which state the steady state is reached late, so on, can be determined easily. Finally, for week 8, lab number 6, this is what we did. We took up a 1D heat conduction problem at steady state. Okay. So we would quickly see what the problem statement was and what how we solve it. So the problem statement was that you have a one-dimensional rod. The rod was maintained at 2 ends at 2 different temperatures. So TB at one end, T at the other end, and then there was possibility of convection. The convection was the rod, convection the environment, and we wanted to know the temperature profile. A temperature profile, what is the temperature at different locations in the rod, right? The model equations were given to you. The model equation was d2x by dt squared plus beta times t infinity minus t is equal to 0. The values of all of these parameters along with the boundary conditions. The boundary conditions in this case, or the initial condition, were given to you. So this is a boundary value problem, although a second order ODE, this was a boundary value problem, not an initial value problem. And we were asked to determine the temperature profile, and there were several parameters associated with the system. So if you vary different parameters, what would happen? And finally, there can be three different boundary conditions which can be defined for such second order ODE. So in one case, the unknowns are given to you at the both ends. In one case, the derivatives are given at both ends. In the third case, mixed boundary condition, which means at one end the derivative is given, the other end the unknown is given. And in under these three conditions, although the equation is the same, you have to solve for different cases. So now, for solving boundary value problems, you need a different function. So BVP5C is the function. Now you should remember, which is needed for solving boundary value problems. And boundary value problem function BVP5C involves three parameters. The boundary value problem function, the exact function, which will give the variation, which gives the exact definition of the differential equation. Boundary condition function, the boundary conditions which you have, and the initial guess. You need to give some initial guess for the solution. So this syntax, I hope you have understood. The function comes from the definition of the derivative or the differential term which you have. In terms of two different, you convert it to two first order ODEs and you give the definition. Then boundary condition equations. So first boundary is 298 Kelvin, the second boundary is 1023 Kelvin. These two were given from the problem, and the initial guess has been given as sin x and cos x. We learned in the lecture why sin x and cos x perhaps makes sense. So if you solve the problem, you must have gotten this temperature profile with initial with one boundary condition, one temperature, the other boundary condition, another temperature. What is the temperature in the intermediate positions? Next, we saw the effect of ambient temperature. The whole point was that you should not have to run this code a lot many times. You should be able to put this solution in a loop, and this graph should have been generated automatically. I hope you were able to do that. And third, and arguably the most interesting observation, three different boundary conditions. You see completely different profiles. In all three conditions, the derivative condition, which is given as the definition in the problem, is satisfied at all the points. The boundary conditions at both the boundaries are satisfied in all the three conditions. So, in the 8 weeks of this course which we have covered, we have already covered how to solve those problems which deal with non-linear algebraic equations, single as well as multiple, simultaneous linear algebraic equations, boundary value problems, as well as initial value problems, both single initial value problem as well as multiple initial value. What you can expect next? Well, very, very interesting problems further. Partial differential equations, both parabolic, which give you the kind of systems which vary both with time as well as space, elliptic systems, which vary only in space but don't vary in time. It is a steady state, multidimensional systems. We'll look at one example, one very interesting problem from optimization, and finally, a very important application, which is curve fitting and nonlinear regression. So, a very quick look into the questions which we have been receiving on the forum as well as the sheet which is circulated. It has been attempted to convert, to find out if there is a way to convert a MATLAB script file to a text file. Now you see, MATLAB script file is essentially a .m file. I'm trying to figure out what might be your thought process? Why did you want to do this? Typically, those who use Linux have a habit of always dealing with a text file, and they want to write the codes and do everything in the text file and simply run the code, right? So one might be interested in actually having a text file and make all the changes in the text file and then import that file in MATLAB to run the file. So there are two, three issues. Direct conversion of a MATLAB.m file to a text file is, at this point of time, the functionality is not provided by MATLAB. However, the live script file, not the .m, but the live script file can be exported to PDF or Word. So if you want to export the live script file for some kind of a demonstration to PDF or Word, that is possible. Furthermore, if you want to run compilers and associated languages in Linux, if you want to run directly a text file in MATLAB, again that's going to create problems. The file name, while it's important, we must understand the file extension also is equally important. The file extension for MATLAB is .m, and you should use .m as the extension, not .txt. Second very interesting question was generating a 2D plot from a 3D surface plot, right? How do you generate? Because this is typically what you must have come across here in this case, right? See, in one of our problem in week number 4, you had 3D plot, and then I also showed 2D plots, right? So how do you actually get one from the other? So one needs to understand the concept. So on the left hand side, you see a sphere, right? A representation of a sphere, and the sphere, if you want a two-dimensional analog of a sphere, the two-dimensional information from a sphere, saying that you want to go from the left side to the right hand side, how exactly does it happen? Well, you don't actually get the same circle, two-dimensional circle, which you see here. Rather, all of these are in fact the two-dimensional plots. How? Because in a three-dimensional system, there are three variables which are changing, and the entire space is filled with all these three variables. Then you need to, in two dimension, you need to choose those variables in which the third variable is a constant. Okay, that's how you get the 2D plot, and in other words, it's called projection. Okay, so how do you get all these circles? How come all these circles are correct solutions, 2D equivalents of this sphere? See, essentially, you are doing this. You are taking the circle, you're taking the sphere, and you are cutting it. Okay, now if I cut the sphere from this far right plane, I'm going to get a small circle. If I cut it from the center, I'm going to get the largest two-dimensional circle, right? So the way you get a 2D plot from a 3D plot depends where you are actually looking at, which section you are looking at. Because in this example, all of this entire section has a constant value of y. Y is constant, x and z are variable, right? So this is essentially what you need to do. You need to find out what is the third variable in my projection. What value should I need to set it to? What should be the constant value for the third variable? And you need to extract only those values from this x, y, z or x, I, y, I, z, I coordinates for which satisfy, say, z, I is equal to 3. All of these cases, z, I will be equal to 3. That subset of x, I, y, I will be taken out, and you can then plot. So this is the principle essentially behind this particular conversion of a 2D plot or obtaining a 2D plot from a 3D plot. So this is what all we had in today to discuss. I am glad that you are continuing your interest in the course. The final 4 weeks would be still more interesting. Uh, thank you. Thank you for joining this live session, and good luck for your endeavors. Thank you.